for the introduction, and thank Mutal and Malte for the invitation. It's a good pleasure to be back to NTU. So today I want to talk about two things about wave equation that will be in 3+1D. One is the basic local existence and uniqueness, and the second is the long-time behavior. In other words, the decay of wave. So here are the references. The first one is for the existence and uniqueness, and the second two is for the decay. So let's start. So let's begin in the Minkowski spacetime. So the standard wave operator box is simply dt squared plus summation I equals from 1 to 3 di squared, where I equals 1, 2, 3 corresponds to x, y, and z, the standard coordinate.
You won't change the sign.
Yes. Thank you very much. Otherwise, that would be the Laplacian operator, which we can written in a more geometric way. We look at the Minkowski metric, dxa, dxb, that's minus dt squared plus summation I goes from 1 to 3 dxi squared, and this is nothing but we contract the Hessian with respect to the metric. In other words, this is the Laplacian with a Lorentzian signature. Therefore, it's straightforward to generalize it to a Lorentzian manifold. G is the Lorentzian metric with signature minus, plus, plus, and plus. Then box G is contract the Hessian with metric. And here, of course, the Hessian is taken with respect to the Levi-Civita connection. So just like the harmonic function is the critical point of the Dirichlet functional, a scalar function, box U equals 0, if only if it's a critical point of the, well, still the Dirichlet functional. G, that's integration, and G upper AB gradient A U gradient B U times the volume form induced by G. And this Dirichlet functional is invariant under the coordinate change, which leads to a stress energy tensor, TAB U, which is of the form dAU dBU minus a half dCU times GAB, which we have already seen in Jordan's lecture. This can be derived by taking the derivative of this Dirichlet energy with respect to the metric. Or we can just take it for granted and compute its divergence. GAB. This will be box U dot with gradient BU. In particular, this will be 0 if U is a solution of the wave equation. And this is the conservation law. And the vector field method, which is a robust way to do the estimate for the wave equation, is simply take some vector field xb. xb is some vector field, and apply the divergence theory. The most typical example is, well, let's go back to the Minkowski spacetime and use the Killing vector field, the timeline Killing vector field, ddt, as the vector. R31 t equals ddt. And let me apologize for my notation. I would like to use T to stand for the stress energy tensor and the Killing, timeline Killing vector field. The difference is if it has two indices, that's the stress energy tensor. If you have one index, that's the vector. Okay. So if we take the divergence, TAB of u contract with TB. If the derivative hits the stress energy tensor, that would be 0, because you satisfy the wave equation. If it hits the Killing vector field, we have TAB, gradient A, TB. And because this is a symmetric two tensor, one can symmetrize this. And ddt is a Killing vector field, which means the symmetrized gradient is 0. So this is 0. Then let's apply it to the region omega, lies between two fixed times, t less or greater or equal to t1, less or equal to t2. Therefore, we have integration t equals t1, TAB, TB, and A dx plus omega TAB, TB, volume is equals T equals T1, TAB, TB, and A dx, where this and A, that's the unit future normal vector. In this case, well, it's the same thing as ddt. But later, we are going to apply it for different space-like hypersurfaces. So let me keep it as n, and it will always mean a normal future vector of certain slice. And we have already discussed that this part is 0. So what is these two pieces? Yes, one is T2. The T2 is over here. Thank you very much. And well, it might be sometimes confused where you should put T1, where you should put T2, but one can look into the divergence theorem and sort it out, and this is the correct. I ensure you this is the correct order. Okay, so what is that integrand? That leads to another property of the stretch energy tensor, which is it satisfies the energy condition. For any future vectors xa and ya, TAB, xa, yb, is always greater or equal to 0. Actually, usually it can be bound by certain derivative of u squared. In this specific case, TAB, TA, TB, this is a half of dtu squared plus summation I equals from 1 to 3 dru squared. And I will just write it as a half u squared, where I use partial to denote the collection of vectors dt, d1, d2, and d3. And I also define the energy of u at time t, t naught to be integration t equals t naught, a half du squared dx. Therefore,
so that's your definition of partial u squared?
Yes, this is definition of partial u squared. And I use partial to denote these standard coordinate vector fields. So to be more precise, that's summation. Summation over every member of u, you take the derivative of summation among every member of vector fields in partial. You take the derivative of u along that direction, take the square, sum over them, and that's the.
But there could be some confusion.
So
because your partial could be this operator. For example, I can write down a du squared.
yes.
And you may just indicate dtu squared instead of all of them.
Okay, so then let me be more precise. Summation. Let's see, x equals d xu squared. Okay. Square dx. So we have the conservation of energy. T2 equals T1. Yes?
Sorry, what was the comment? Second line from the top in the parentheses, second line from the top?
This here?
What was the comment there? Sorry, I missed that.
So here, first, the energy condition says if you contract it with two future vectors, that's always non-negative. And in most of the cases, it will be bounded from below by du squared. But what it is precisely depends on which direction x and y is. And we will come back to it later.
Maybe you explain the notation.
Oh, this notation? Okay, so this notation, I will. A is greater or equal to B, if there exists a constant C such that CA is greater or equal to B.
Thank you.
Okay. So that's the conservation of energy. And we can also see the finite speed of propagation from this kind of discussion. Here we use the divergence theorem in the domain omega like this. So that's between two time slices, t equals t2, t equals t1. If instead we look at this region, t equals t2, t equals t1, and here is r less or equal to r naught, here is r less or equal to r naught plus t2 minus t1. Then when applying the divergence theorem, there will be three boundary terms. One on the top, there will be second on the sides. Well, here I suppress 2 dimensions, so each point we should really think rotate this picture along the axis. So there will be another contribution on the sides and the one on the bottom. Divergence theory. Will tell us 1 plus 2 equals 3. And let me be more precise about what is this 2. Let me denote this by I is the integration along the hypersurface I, TAB, TA, L lower bar B times volume, L lower bar. I need to lower the index, where the L lower bar is the incoming, now killing vector. Sorry, incoming, now vector. L lower bar is dt minus dr. So when dealing with divergence theorem in the Lorentz space-time, it's always confusion. You're always confused when you deal with the null hypersurfaces, because, well, for these hypersurfaces, you don't have the induced metric degenerate, so you don't have the natural volume form.
What's the notation?
DUL.
In the integral. What is the integral?
TAB, TA, that's
Not the integral.
the volume form.
Oh, that's volume. Okay.
Volume.
That's VOL.
VOL, the volume form, but the one induced by L lower bar. So here, the VOL, L lower bar is a 3 form, such that if this is the vector field, make it 1 form, wedge with dVOL, L lower bar. This needs to be the space-time volume form. And this is the correct notion if you want to apply the divergence theorem in this form. So this becomes a 3 form.
If you define a 3 form, you're going to use L bar lower sharp.
Yes, because, well, one form, which is a 3 form, becomes a 4th form.
Yeah, but just in terms of notation, you have D bar
L lower bar sharp.
And there you have D bar
Yes.
L lower bar.
Yes, thank you very much.
And the other one
Yes.
should be L lower bar.
Yes, L lower bar sharp. Well, if you look at this, it has some certain ambiguity in defining this. There will be a bunch of 3 forms satisfy these conditions, but alone, the non-hypersurface I, all of them will give you the same 3 form. When you
How do you use L bar lower sharp?
So L bar is a normal vector of this now hypersurface. That's a normal vector.
Right, but what do you use as sharp? What is that?
So sharp means this is a vector. I want to lower the index, make it a 1 form. Make it a 1 form. So let's look at what is this piece. And to do that, the easiest way is actually to decompose T into the null directions. Let me define L to be T plus dr, the outgoing null vector. Then if I contract TAB with LA, LB, this is very easy to compute. It's greater than L U squared, because the second piece of the search tensor will have no contribution. L is a null vector. And TAB, L bar A, L bar B is the same. And TAB, L bar A, L B, that's the angular part. This is have 1 over r squared d theta u squared plus sine minus 2 theta d phi u squared. Well, the last one requires some computation. If you contract T with L bar L, the first term give you LU times L lower bar U, and the second term give you gradient U contract with gradient U. The radial part, the L and L lower bar part will actually cancel, and you are left with the angular part, the angular derivative U contract with itself. Okay. So now let's decompose T into the L and L lower bar direction. That's TAB. A half L plus L lower bar A times L lower bar B. If we have L lower bar, that's L lower bar B, which in particular is non-negative. Therefore, in particular, if U equals 0 in T equals T1, R less than equal to R naught plus T2 minus T1, and its time derivative also vanishes, then U is at equal 0. In this domain, this is the finite speed of propagation. Okay, now let's talk about the existence and uniqueness of a solution of wave equation. We're going to use that not only in Minkowski, but for general Lorentzian manifold. However, through the finite speed of propagation, everything can be localized. So we can still assume we are in the Minkowski spacetime. And we look at the operator P, that's minus dt squared plus g tilde ij di dj plus d0 dt plus b tilde I di plus c tilde, where we will always make the assumption. First, this part, g tilde ij, is Riemannian and is uniformly elliptic. It's lambda, small m, capital lambda, such that g upper ij is bounded by these two constants. Second, we are going to assume every coefficient is smooth with bounded ck norm. There exists constant ck such that g tilde ij, b tilde 0, b tilde I, and c tilde. Their ck norm, may be more precise, in the whole R4, just for convenience, is bounded. In a general Lorentzian manifold, one can locally write down a coordinate system such that the wave operator takes this form. And in fact, for wave operator, you don't have this c tilde term. So we want to show there exists a solution of this operator. To do that, we need an a priori estimate. So fix a regularity, S in Z, and fix a time. There exists a constant, C depends on S, T, and all these constants, such that, suppose we have a function U that's in C0, go to T, maps to HS plus 1, of R3 intersect with C1 equal to T HS R3, and PU is in L1 equal to T HS R3. Then we have the estimate. Summation alpha is equal to 1, the alpha u, its HS norm is bounded by this constant C times summation alpha s we equal to 1, the alpha u HS plus integration 0 to T. The HS norm of PU at time t prom okay, it is an a priori estimate because already assume certain regularity of U. U is in C0 of this and C1 of this. And all these HS or L2 norms are computed with respect to R3. And well, later I will omit the R3 part.
There should be some mistake in notation. Put it inside technically, this is right.
Thank you very much. So that's for any t from 0 to t. In other words, if in particular U is a solution, then initial HS norm control the later HS norm. So this SS norm, HS space, that's the W to H space. That's the space where, for the function U, whose integration in R3 alpha less than or equal to 2. Sorry, alpha less than or equal to WKP. Sorry, this is S2. I want to take S number of derivatives. So for S, equal to S, d alpha u squared dx is less than infinity, and HS norm is exactly the square root of this quantity. And if x is negative, well, one could define it through the Fourier transform.
The notation C0, C1.
So yeah, C0, here we have a Banach space, and so C0 to this U can be considered as a continuous map from 0 to t, that's the t variable, to this Banach space. And C1 means, well, you can take one derivative, and it's still in HSR3. And the L1 means, this part is the L1 norm of PU. You take the norm of this Banach space, PU of HS, and we look at the L1, so we integrate it. And this assumption is nothing but, well, this quantity is bounded. Sorry?
Write the most.
Here? Oh, no, this is S, because here we have the derivative up to 1.
And that's the second derivative.
Yeah, that's the second derivative. So, well, in the elliptic estimate, you get two derivatives. If you assume Laplacian U is in L2, then U is in W22. However, in general, in particular for the wave equation, usually you just get one derivative. So if I assume PU is in HS, well, the best we can say is U is in S plus 1. So here we have one more derivative. So I'm not going to prove the whole theorem. I'm going to show you the case for S equals 0. So the proof is actually very similar to the conservation of energy. But now the principal symbol is different, but that's not a big deal. We just define our Lorentzian metric to be -1 and G tilde ij. Then box GU is PU plus some lower order term, B0, dt plus di plus c. And all the ck norm of this piece will be bounded. The difference will be some Christopher symbol of Lorentzian metric G, which is bounded by the second assumption. Then apply the divergence theorem to TAP U TP, where this T is still ddt. This guy is not Killing vector field for G, but let's see what would happen. And I want to apply it in the domain omega. That's 0 less than equal to T less than equal to T1. Therefore, integration T equals T1, TAB, TA and B, the volume, and G plus the divergence, TAB, TB, the volume G, equals the integration on the initial slice of this integrand. So let me explain the notation. I'm applying the divergence theorem, but not with respect to flat metric, with respect to this Lorentzian metric, G tilde. So this n is the normal vector with respect to g tilde. In general, that's not ddt, as well as this 3 form and this 4th form. However, it's not standard by the first assumption. G tilde, the remaining part is uniformly elliptic, so this is comparable to the standard 3 form dx, and this is comparable to the standard space-time volume form dx, dt, dx, dy, and dz. Also, this part, by the first assumption, is comparable to, well, let me still use my confusing notation. Du squared, that's dt u squared plus the summation I from 1 to 3 di u squared. So here we get back to our energy E as well as over here, except that we might not need to put some constant everywhere. So what is this part? The bulk term in divergence. So let's compute it. Divergence of TAB, TB, that's box GU times DTU plus TAB times DATB. Now this term is not 0, again, because ddt is not a Killian vector, so I need to keep it. And box U can be written as PU, DTU, plus the rest terms, D0, DTU, plus DI, DIU, plus CU, times DTU, plus TAB, okay. Now let's take the absolute value of everything. The first term is Pu. We can do nothing about it, so let's just keep it. Pu times Tu. And what's the structure of the rest terms? It will involve only up to the first derivative of u. You can involve dtu, diu, there's dtu over here, or in the stretch energy tensor, I already erased that, but it only involved the first derivative. So it can be bounded by c times b less equal to 1 u squared. Here I need to include the base term because the presence of cu over here. And this constant will depend on the constants over there, if you keep track of it. Okay, now let's throw everything back to divergence theorem. This tells us du at time t1 is bounded from above by a constant c times du at time 0 plus integration from 0 to t1. And this part, let's just write it as its L2 norm, d less equal to 1 u L2 plus, and for this part we can use Cauchy-Schwarz to bound it, L2 norm squared by du L2 norm times the L2 norm of Pu. Okay, this is almost what we want. We want to control the L2 norm of du, except that in the definition of EU, we don't have the base term. We only control the derivative, but not u itself. But it's fairly easy to add the base term by the fundamental theorem of calculus, dtx, that's u0x plus integration 0 to t dtu from. Therefore, the L2 norm of u is bounded by 2 times L2 norm at time t, L2 norm of u at time 0 plus 2 times t times integration of L2 norm of dtu. But we are allowed to put to make our constant c depends on capital T. So this t is not a problem for us right now. Then we add these two estimates and define the tilde u to be half u squared plus u squared x. What we end up is e tilde u at time t1 is bounded by a constant c times e tilde u at time 0 plus integration 0 to t. We have e tilde u itself from this part. Plus the L2 norm of Pu times e tilde u. Take the square root. We end up with an integral inequality, and this is a place to apply ground wall inequality, or put it another way, the ground wall inequality tells what it says is you just define the right-hand side to be a function ht1. Then by taking the derivative of ht1, you see e tilde of here and here. And you already know e tilde is bounded by ht1. In other words, by defining this as ht1, you can rewrite this as a differential inequality. And you can integrate that differential inequality. dt e to the minus c over 2 t ht. It will be bounded by the L2 norm of Pu. Integrated, ht is bounded by e to the c over 2t times h0 plus integration 0 to t Pu L2 dt prime. And finally, h0 is nothing but e tilde u at time 0, and e tilde u at time t is bounded by ht. So put it back, we arrive at the desired a priori estimate for s equals 0. And once you have that, it's fairly easy to get for s larger or equal to 1. You simply commute everything with the derivative along the x direction. Commute. Alpha x. You define the alpha xu equals v. If this is just the standard wave operator, it will commute with dx and everything follows. And if it is not, as in our case, well, we assume the derivative, everything has uniform ck norm, so everything goes through. And for negative x, what one can do is to use the integral operator. Define v as I minus the spatial Laplacian to the power minus times u. This will tell you the the positive hs norm of v is comparable to the hs norm of u. Then one apply the theorem for v and try to translate it to the statement of u. Then that's so if you want to see the detail, you can look at the lecture note of Sagi. Okay, so this is the a priori estimate. We have the control of later hs norm by the initial hs norm and this piece. Now it's the time to talk about the Cauchy problem. So we want to solve the wave equation by prescribing the initial condition and the source. First, Pu equals a source f tx with the initial condition u0 x equals a function fx, and dt u0x is another function gx. And at other PDs, one can define the weak solution. U is a weak solution if it satisfies this in the integral sense. In the weak solution, in 0 to t equals R3, if for any smooth function with compact support, 0 t, we have 0 to t R3 phi times f dx dt is equals 0 to t R3 p star acting on phi times u x plus other boundary terms. So here what happens if, let's just pretend u is smooth, f p is an operator, over here, minus dt squared. Then one can do the integration by part. One end up with some operation on phi. This is the formal adjoint of p, denoted by p star. And in doing so, in particular, when you do the integration by part along the t direction, you will pick up the boundary term at t equals 0. And, well, you can work it out to see what they are. At the end, one use this as the definition of a weak solution. If you throw in a test function, a smooth function with compact support, and here I want it to be at equal to 0 at time capital T, then it satisfies this equality. Now we can state the existence and uniqueness theorem. Again, let's fix a regularity S, which is positive, and the time Then for any data, f, g, and capital F, small f is in hs plus 1, g is in hs, and capital F is in L1, T, hs. There exists a unique weak solution of star U, and that's in the suitable space C0, T, hs plus 1, and C1, T, hs. And the proof goes by using the theorem 1 and Reed's representation theory. Let me give you a sketch. So the step 1 is to assume this data is smooth with compact support. Furthermore, we can also assume initial data, f and g, are 0. And fix a regularity as n. Apply theorem 1 to the test function. Apply. To the test function phi, which is smooth with compact support. 0t, and the not p but the adjoint operator. So we have the h minus s norm of phi at time t is less or equal to a constant c times integration 0 to capital T p star phi h minus s t prom dt prom. Now let's define the space p star acting on the smooth function with compact support R3, which is a subspace of L1 HS. Because, well, here we have smooth function with compact support. When you're acting on throwing a differential operator, it's still smooth function with compact support. Define the linear functional LF acting on P star phi to be how we define the weak solution 0 to T 3 phi times F to X dt. Then by the a priori estimate, the size of this linear functional is bounded by 0 to T phi h minus s f hs dt, and h minus s is bounded in this way, c times in other words, this LF is a bounded linear functional defined on this subspace V. Then by Hahn-Banach's theorem, one can extend this functional to the whole space L1 0 to t to hs. Extend f to then by Reed's representation theory, Vf of psi can be written as 0 to t r3 psi times u dx dt. In other words, u is a weak solution where u is in the dual space by infinity. H here's minus s. Sorry, here's minus s. S. And this holds for every s. We can, therefore, u belongs to C infinity. Let me be more precise. That's C infinity in the spatial direction. Then one can use the equation to upgrade the regularity.
So you say when you say without loss of generality, you can actually change your capital F.
Yes. Well, okay.
To absorb the,
Yeah, to absorb the initial term. Yes.
in the case where capital F is equal to 0, your F is actually completely equal to 0, is it?
If capital F equals 0, yes, the solution will be completely 0.
Okay, of course, your
And one can show it by the energy estimate.
well, but because you're assuming that the G are both equal to 0.
Yes.
So that actually corresponds to the uniqueness.
Yeah, that's the uniqueness part. So here I focus on the existence part. When define these bounded linear functional by Reed's representation, one has this representation u. One can use any s, so that's actually smooth in the spatial direction, and one can use the equation to upgrade the regularity. But let me omit that part. So this is step 1 when every data is smooth with compressed support, and step 2 is just by approximation. And let me explain this part by words. So for general data, you can approximate by smooth function with compressed support. What you have is a bunch of smooth functions satisfy the wave equation. Because they are smooth, you are allowed to use the a priori estimate, and you show that they converge in the suitable space. So that's the local existence of linear wave equation. Okay, any question? So this is the first part of this lecture. Now let's move to the second part. What would the solution be when time goes to infinity? Well, you might ask, why can here we don't assume anything on capital T? One can just make T goes to infinity. What would happen? The thing is, the constant here depends on T. In particular here, if you want to control the base term, you need to throw in this factor T, which deteriorate when T goes to infinity. And when we look at the long time, we want something independent of T. Well, even better, it decays with respect to T. So let's start with what we want. And let me be clear, from now on, we are in the Minkowski space-time. And we solve the standard wave equation, box U equals 0, with an initial condition, U 0, x, that's fx, in h1, and its time derivative, is in L1. From the existence theorem, we have the solution, which is we have C0 from 0 to infinity to H1 and C1 for each time that's in L2. Okay. We already know the energy is conserved. U T U0. Which is nice, but it does not control the base L2 norm. In particular, if you take the constant function 1, well, this energy will be identically 0. Its derivative will be 0. So it says nothing about the constant function 1, even though it's actually excluded from the initial data. So to remedy that, let's use this simple lemma. 3. Suppose f is a function. Is on R3, and suppose drf, r derivative f, is in L2, and r minus 1 times f is also in L2, where this notation, r bracket, that's 1 plus r. We just want to avoid the singularity at r equals 1. Then the L2 norm of r minus 1f is bounded by the 4 times the L2 norm of drf. This can be proved by the Hardy inequality, but I will take this for granted. By using that, the space we actually want to assume is f is in H dot H1 intersect with r times L2. And instead of this energy E, we want to define the one with a base term, EP, U, T, that's a half u squared plus r minus 2 u squared dx. Then we can upgrade this boundiness to include the base term, dB u at time t is controlled by the initial EB energy. And if we, so the constant here is actually 8, but again, I will use this notation. If there's some constant, to put it on the right-hand side, such that the right side is greater than the left-hand side, I will denote it by this. One direct corollary is now we can control the sum norm of U if we throw in, if we commute the equation with angular Killing vector fields. Suppose omega, that's omega 1, omega 2, omega 3. The one basis of angular Killing vector field, omega 1 can be dV, and there you need another 2 to generate the whole space. Suppose omega less or equal to 2 fx is in that space, h dot 1 intersect with r L2. This is in L2. Then the absolute value of U, I put square over here, is controlled by r to the let me see, -1 times EB energy of less or equal to U at the initial time. In other words, the solution would be bounded.
Your space H dot 1 intersect RL2 is just the space where EB is.
Yeah, where EB is bounded. Yeah, the space where EB is bounded. Okay. Why that's the case? So we want to control R times U squared. Fix R naught greater or equal to 0. If R is less than 0, this is equivalent to 1. R naught times U R naught squared. Just use the Sobolev inequality on the standard sphere integration. S2 R naught. This part is the same. R naught times dv tilde. Where this dv tilde we have seen in the lecture last week. That's the standard volume form, the unit sphere. Sine theta d theta d phi. In particular, there's no factor of R in it. So let's look at the base term in this expression. S2 R naught times U squared dv tilde. Let's use the fundamental theory of calculus. Take the R derivative and integrate to the infinity. R naught to infinity. S to R. When derivative hits R naught, that's U squared. When the derivative hits U, we have R times twice U times dRU dv tilde dr. Yes, here I put the less or equal. Well, you might ask what's the another boundary term at the infinity. If you look closely by those equations, by the boundedness of EB, it will actually implies that one can choose a subsequence such that this quantity, if you take R naught goes to infinity, that would be 0. So that's what really happens here. There will be no boundary term at infinity. Okay. So this is not the volume form on R3. One need to put extra factor, R squared, over here. So let's divide it over R squared. And here I change it to R to the -1. And we can see this term already appears in the EB energy. That's R3 times R to the -2 U squared plus, and here we simply use Cauchy-Schwarz. One will give you exactly the same term, another is dr U squared dx, which is EBU at a certain time, t at time t, and we already have the boundedness at time 0. Then you commute with angular vector fields and somewhere up. When arrive at the boundedness estimate. Okay, any question? But still, we do not see the decay of it. Everything is bounded right now. To see the decay, actually, we need to go to non-infinity. We want to take another size. Before doing that, yes.
For
that's 2 dimension. I need Kp, like n, and P is 2, n is 2, and let's see, Kp, P is 2, n is 2. Yeah, if that's 1, that's equality, that's exactly the borderline. Just be safe, I put 2. K is the number of derivative, P is the LP norm, n is the dimension, and S2, n equals 2, P equals 2, that's L2 based, and if I put K equals 1, that's 2 equals 2, that's the borderline.
That's just a simple formula.
Oh, you mean, so here I didn't assume U is supported on the, let me think. Let me use the Poincare inequality. The Poincare inequality controls the L2 norm of U along the sphere. Here's the L infinity norm.
Oh,
Yeah, here
this is Sobolev.
yeah, this is Sobolev, not the Poincare inequality. Yeah. Okay. So. Now let me discuss the integrated decay estimate, the Horowitz. And to simplify the computation, let me use this notation. You know, quantity A is equivalent to B if A equals, there exists one form, B A, and a function, smooth function F, function, such that A equals B plus the divergence of BA plus F times U squared. Let me give you an example. For any smooth function F, we can take the divergence of F dA U squared minus dA F times U squared. Through some computation, you will end up with F times 2F gradient Cu plus 2F times box U times U. And again, we always assume U is the solution of the wave equation. We don't have this term. In other words, gradient U contract with gradient U is actually divergence. So in my notation, Cu, F. The idea is later when we use the divergence theorem, we want to compute what is the bulk term. And when we're dealing with the bulk term, we can always add a divergence. That will add some contribution on the boundary. And let's not consider that for a moment. And sometimes we have the base term U squared. And just for the simplicity, let me also ignore them. I also only want to consider the first order term, the first derivative term. Okay. Now, the Horowitz estimate is by using A, that's R. So what would be the divergence? Gradient A, TAB, R, that's TAB times the Hessian of R. And if you compute the Hessian of R, it'll be 0, and that will be 1 over R over R squared over R squared sin theta G. And this is in the coordinate T, R, theta, and phi. Oh, it's not surprising to see this part. This is the, well, second fundamental form. And I just want to say all other terms would be 0. So that's proportional to the metric on the orbit sphere, and the factor is 1 over r. Okay, so let's contract TAB with this part. Well, under this notation, TAB, let me write it again. TAB, that's u minus a half. Well, this part is not important. This part is equivalent to 0 under this notation. So, contract with the angular metric.
This definition here,
Yes.
the notation here is just for scalar.
Yes, for
Now
scalar.
you want to apply to tensor.
So what I actually mean is whenever you contract it, here I do the contraction, you get something over here, but that's gradient u, but that's equivalent to 0. So that part is not important. It's just to simplify the computation. So this will be 1 over r times u squared, which is non-negative. If this is actually the case, here this equivalence. If this is not just the equivalence, but an exact equality. If then we apply the divergence theorem in the region. T1 that's equal to T. R, where is R? I have R over here.
Inside the parentheses.
Yeah, I think that parentheses. Thank you. We have integration. T equals T1, TAB, gradient dr, and A, dx, plus. It is region omega. 1 over R, u squared, the volume, equals T equals, this is T2, and this is T1. Dx. So this time, we have a good sign in the bulk. The bulk term is positive, but, well, we don't have a good sign for the boundary. But this is already controlled by the previous step. If you write it out, what is this? TAB, gradient AR, and B. That's, again, let me decompose it into the non-directions. T, L plus L bar, L minus L bar. So that's a quarter, gradient L, u squared minus a quarter, gradient L bar u squared. The explicit expression is actually not important. The important is, well, that's some du squared. So this piece is controlled by EBU. Which is already bounded. And of course here, as I said, I already store away all the low order terms, and as well as the divergence term. So let me tell you what is exactly true. Define the current. This is F times TAB, gradient dr, minus a quarter with an a omega u squared plus a quarter omega. With the choice f, that's 1 minus r to the minus 1, and omega, that's 2 over r times f. Then the divergence of this current, A, is bounded from below by 1 over r cubed du squared plus 1 over r. The angular direction has a better weight, that's just 1 over r plus 1 over r cubed. So we have already seen the this part, the angular part, 1 over r, gradient slash u squared, and this f is chosen to contribute to the first term. And one actually need to be very careful to make sure you have a positive lower order term, but I will not going to do it here. So that's the Morowitz estimate. The first term is, in general, that's 1 over r cubed. Sorry, here. Sorry, here. 1 over r squared. That's what. So if you integrate it, you will get that the integration of this in the space-time is bounded because the EB energy is bounded. But still, that's some boundedness. To actually see the decay, we need to use the RP estimate discovered by Darfomers and Broniansky. And it is about to look at this current. Define u bar to be r times u. Recall L, that's dt plus dr. Define j prime p a to be r to the p minus 2 times tab u bar times lb. And its divergence will be from A, that's P over 2, L u bar squared times R P minus 3, plus a half 2 minus P. The angular derivative of u bar squared with weight R to the P minus 3. Again, let me just show you by focusing on the first derivative terms. Here P can be any number, but to make this part positive, later we will choose P to lies between 0 and 2. Or P minus 2, P at B, bar B. And in doing this, we are going to need the Laplacian of u bar. Plus 2. This part is 0 because you satisfy the wave equation. And this part is lower order term, so let me also ignore that. That's 2 over r dr bar. And this is 1 over r u minus it's convenient to write everything in the null directions. Okay, so it has 3 terms. Yeah, the last one is u bar. I want to express everything in terms of u bar. So that's p minus 2 times r to the p minus 3 times TAB. Contrast with L. We have gradient R. Gradient R is a half L minus L bar. Plus, when the derivative hits the stress energy tensor, that's R. And we already know what is box U bar. That's 1 over R, L U, minus gradient L bar U. And we have another piece, that's L U bar, coming from this L. Plus, when the derivative hits L, but what is L? L is T plus ddr, and T is killing, has no contribution. And R, as we already discussed, that's only the angular direction here. R, P minus 2, and 1 over R. Okay, let's collect terms. For LL, we have gradient L U squared. This term and this term becomes, we have the factor 2 over here is p minus 2, but we have another 2 coming from the second line. So that's just p minus 2. And for the other 2, here we have gradient L U times gradient L lower bar U. But under this convention, this is actually equivalent to U squared because CU, that's minus gradient UL, gradient lower bar L plus U squared. So here I have bar, bar. And the coefficient will be minus 3 over 2. The last one is plus 1. Everything times r to the p minus 3. We write it as gradient, the angular gradient. So that's e over 2 plus half. So of course, this is only the first order term. To be more precise, one need to be patient to compute everything out. But this is the case. So in the range p lies between 0 and 2, the divergence would be positive. And what about the boundary term? As I said, to see the decay, we need to go to non-infinity. So let's fix a number R naught greater or equal to 1. And for any tau, let's define sigma tau to be t equals tau when R is less equal to R naught union t equals tau minus t minus R equals tau minus R naught when R is greater or equal to R naught. So it's easier to see it from the picture. So this is the Penrose diagram for the Minkowski space-time. This straight line is R equals 0. So this horizontal line represents t equals 0. And I want to go to go along t equals constant and add certain radius. This is R equals R naught. It becomes null. this one is sigma 0. And furthermore, let me denote this part by sigma 0 double prime, and the null part to be sigma 0 prime. Okay, so what's the advantage? The advantage is we are going to apply this RP current just for our large range. So to modify it, I need to times everything by a cutoff function eta. Eta equals 1, then r greater or equal to r naught plus 1 and 0. So the boundary term J from P A dot is A will be R to the E minus 2 times L bar squared, because times L. Because in the null part, we are going to choose our normal vector to be L. Therefore, here we have TAB contract with double L. That's just the L direction of the this U bar inside. Compare with its divergence, exact the same term. Almost appear in the divergence, except that instead of P minus 2, there it becomes P minus 3. So the order is lower. Okay, now we can combine everything we have. I forgot to define the T current. T current is simply TAB contrast with TB. Now we define JP to be Jm, the Morris current over there, plus a constant times the T current, plus a small but positive constant times J prime P. Let me just say in words, what's the purpose of this large and small constant? We need to put epsilon here because, well, when we compute the divergence, including this eta, it will no longer be positive. We have some lower order, some error term in the transition region of eta. And that's where the Morris estimate is quite useful. We have some positive term. We can choose epsilon to very small to absorb those error terms. That's the purpose of this small epsilon. And the CT, and this large constant CT is to make sure that the boundary term is positive. Remember, in the Morris estimate, the boundary term does not have a sign, but we can add a huge constant of T to make it positive. So the conclusion is for any P belongs to 0 to 2, divergence of JP would be non-negative. And the boundary term, sigma tau JP dot N, dividing N sharp, is equivalent to the following norm. On the space-like part, that's still du squared plus r to the minus 2 u squared dx, essentially because this large constant Ct. And on the null part, sigma tau prime, we have the L u squared plus the angular part plus r minus 2. This is still the T energy. The T energy along the null part well, you don't have every direction. You have the L and angular part, but you don't have the L lower bar. And finally, that's the RP part, RP minus 2, L P bar squared. And let me define this to be EP of U bar. So this is the boundary term. What about the bulk term? The bulk term, well, is always non-negative, but when P belongs to 1 and 2, integration, tau 2, this is bounded from below by integration tau from tau 1 to tau 2, E bar P minus 1, U tau d tau. Here I forgot to define this D. D0 tau represents the region bounded by two of these space-like null hypersurfaces. So let's look at why this is the case. For this term, well, that's already seen in the divergence of the RP current. That's P minus 3, so it becomes, instead of P minus 2, so here that's P minus 1. What about the other terms? This part, and can be taken care of by the Morowitz estimate. In the Morowitz estimate, we have some positivity. It deteriorates when R goes to infinity, but in the boundary region, it is as good as the term over here. And for these three terms, it's actually a little bit messy. One needs to use Hardy inequality to integrate by parts several times. But let's don't worry about it. This is correct. Okay, so well, what do we have at the very end? So by applying the divergence theory, we have EP of U at tau 2 plus integration from tau 1 to tau 2, EP minus 1 U, d tau is bounded by EP, or have bar at the initial time. This is for P belongs to 1 and 2. And in general, EP is bounded. Tau 2 is bounded by its energy at time tau 1. Therefore, immediately we can see the E2 energy is bounded just by the second one, and E2 energy is bounded. Then the integration of E1 energy is bounded. More or less, it decays like 1 over tau. To make it precise, one need to go back to say, well, E1 energy is bounded by itself. Tau minus 1. And do it again for E0. The E0 energy will decay like tau to the minus 2. Okay, let me finish this by the final corollary. Just like when we know the EB energy is bounded, the subnorm of U is bounded. Now we know the E0 is bounded, therefore it is bounded by R squared minus 1 tau minus 2 times E bar. I need to put 2 over here, omega, that's equal to U at time 0. So the solution of wave equation, suppose it's compactly supported to make sure the left-hand side is bounded. Then its subnorm decays like tau to the minus 2 when t goes to infinity, and decays like r to the minus 1 when r goes to infinity. Okay, any question?
You can actually put everything together into a single vector field and then just
Yeah, but
define the corresponding curve.
yeah, that's exactly what happens over here. Yeah, each one is a current with certain vector field. When you add them together, it becomes a one single vector field.
Just in JAM, you can just choose your omega.
Choose omega, yes. Okay, if there's no question, let me stop here, and thank you for your attention.
So next now we will resume at S2.
如果是老师 maybe 等于说我用个猫面的，然后乘上那个 r 的话，就是 r 就是换成 distance function 的，应该全部都对。
我换成是 distant function。我说这边，我想一下啊 ，micro
你是需要 r 的那个 r 的。
这边是 r 的 Hessian， 不过这边其实我不知道如果用那个 micro local 会比较简，因为 micro local 好像是只 care first highest order term，highest order term 的话其实不是那么难让它有 sign，然后难让它有 sign 的是 low order term， 这边全部都 ignore 啊。
可是你说这 RP 用直接用 micro local，
对，
你还是知道那个 R
没有，这边还是那个，这边我只是为了计算方便，我就只算highest order term，我就 low order